Good morning, everyone, and welcome to today's presentation. I'm delighted to have you here. Today, we will be exploring the efficacy and limitations of 70% isopropyl alcohol in aseptic processing. My name is Dr. S.K. Singh, and I hold a PhD in this field. Over the next few minutes, we'll look into how this disinfectant works, its strengths, and some of the challenges we need to be aware of. So let's get started and dive into the topic. Let's start with the introduction. Aseptic processing is all about maintaining a sterile environment, and that requires a very strict contamination control strategy, or CCS. This is essential to ensure product safety and quality. One of the most widely used disinfectants in these settings is 70% isopropyl alcohol, or IPA. It plays a crucial role in surface disinfection, helping to eliminate potential contaminants on work surfaces. IPA is also used for glove sanitization, which is vital because gloves are a primary barrier to contamination. Keeping gloves clean helps protect the entire aseptic process. Additionally, it's used for equipment cleaning, ensuring that all tools and machinery are free of microbes before they come into contact with sterile products. Because of its effectiveness and versatility, IPA is considered a routine disinfectant, especially in grade A and B areas, where the highest levels of cleanliness are required. Overall, understanding how and when to use IPA is key to maintaining a contamination-free environment in aseptic processing. Let's take a closer look at regulatory expectations for disinfectants. First, it's essential that disinfectants are both qualified and validated before they are used. This means they need to be thoroughly tested to ensure they work effectively and consistently. Additionally, they must be suitable for their intended use, whether that's cleaning surfaces, equipment, or other areas within a facility. Now, moving to the key requirements, these are critical for compliance and safety. The disinfectant must demonstrate proven microbial efficacy, meaning it effectively kills or inactivates the microorganisms it's supposed to. This is fundamental to maintaining a safe environment. Another important point is the rotation with sporicidal agents. This practice helps prevent the development of resistant microbes, ensuring ongoing effectiveness of your disinfection program. Lastly, controlling residues and toxicity is vital. You want to make sure that after disinfection, no harmful residues remain, and that the disinfectant doesn't pose toxicity risks to people or the environment. All these points tie back to our overall goal, ensuring safety, compliance, and effective microbial control in our facilities. So let's talk about how IPA actually works. Essentially, it acts through two main mechanisms. First, it denatures proteins, which means it unfolds and inactivates them, disrupting their normal function. Second, it disrupts the lipid membranes of cells, effectively breaking down the barriers that keep cells intact. Now, water plays a crucial role here. About 30% of the IPA solution is water, and this actually helps improve two key aspects. It enhances cell penetration, allowing the IPA to reach and affect microbes more effectively, and it boosts the efficiency of protein coagulation, making the disinfection process more effective overall. The optimal concentration of IPA for disinfection purposes is generally between 60 and 80%, with 70% being considered ideal. This balance ensures that we get the best combination of protein denaturation and membrane disruption, leading to effective microbial kill rates. So, understanding these mechanisms helps us appreciate why the right concentration and composition are vital for effective disinfection, especially in clinical and sterilization settings. Let's take a closer look at the spectrum of efficacy for this disinfectant. It is effective against a variety of microorganisms, including gram-positive bacteria, gram-negative bacteria, fungi, and enveloped viruses. This broad range makes it quite versatile in different disinfection scenarios. However, it's important to recognize its limitations as well. It is not effective against bacterial spores or some non-enveloped viruses, which can be more resistant to disinfectants. Because of its effectiveness profile, it is classified as an intermediate-level disinfectant. This means it offers a good balance of efficacy for many common pathogens, but may not be sufficient for sterilization or for highly resistant organisms. Understanding these distinctions helps us choose the right disinfectant for the specific needs of each situation, ensuring safety and effectiveness in infection control. Now, let's talk about efficacy validation according to USP 1072. When we validate disinfectants or sterilants, there are several key studies we need to perform. First is the suspension test, which evaluates how effectively the product can kill microorganisms in a liquid suspension. Then, there's the surface challenge test, which simulates real-world conditions by testing the product's ability to disinfect surfaces. Finally, environmental monitoring comparison helps us understand how well the disinfectant performs in actual cleanroom environments. The most important parameter in these studies is the log reduction of microorganisms. This means measuring how many microbes are eliminated, with higher log reductions indicating more effective disinfection. Understanding the role of these disinfectants in aseptic processing is crucial. They are used in Grade A areas, which are typically laminar airflow zones, and in Grade B backgrounds, providing a sterile environment for critical operations. Their applications are quite broad but essential. They are used frequently for gloves disinfection, to prevent contamination from operators. They are also vital for equipment transfer sanitization and surface wiping, ensuring all contact points remain sterile. Ultimately, these disinfectants are critical for contamination control, especially when it comes to protecting operators and maintaining the integrity of the aseptic environment. Their proper validation and use are fundamental to ensuring patient safety and product quality. Let's take a closer look at the log reduction calculation. The formula is quite straightforward. Log reduction equals log base 10 of the initial count divided by the final count. For example, if we start with a load of 10 to the 6th power, or 1 million CFUs, and after treatment we're down to 10 to the 3rd, or 1,000 CFUs, we can apply the formula. So, it becomes log 10 of 10.6 divided by 10.3, which simplifies to log 10 of 10.3. And since log 10 of 10.3 equals 3, we see a 3 log reduction. This is important because achieving this level of reduction typically meets USB acceptance criteria for surface disinfection. Now, looking at our surface efficacy study example, initially, we had 1 million CFUs of Staphylococcus aureus. After applying our IPA treatment, the count drops to about 1,000 CFUs. This indicates a significant microbial reduction, which is a strong indicator of the effectiveness of the disinfectant. So, in summary, the log reduction helps us quantify how effectively a treatment decreases microbial load, and in this case, it confirms that our process meets the required standards. Now, let's take a look at some of the key advantages of this disinfectant, especially in terms of efficacy. One of the biggest strengths is its ability to rapidly kill microbes, which is crucial in maintaining a sterile environment. It also leaves no residue behind, so it won't interfere with subsequent processes or compromise surface integrity. Additionally, it evaporates quickly, helping to save time during cleaning routines. Another important point is that this disinfectant is compatible with cleanroom materials, meaning it won't damage sensitive surfaces or equipment. Plus, it's safe for frequent use on gloves, which is essential for personnel safety and repeated disinfection cycles. Moving on to application specifics, the contact time is straightforward. The surface needs to stay visibly wet to ensure effective disinfection. Typically, you're looking at a contact time of about 30 seconds to 1 minute. However, it's important to remember that efficacy can be affected by a few factors. Organic matter like dirt or bodily fluids can reduce effectiveness, so surfaces should be as clean as possible beforehand. The type of surface also matters. Some materials may require longer contact times or different application techniques. And finally, how you apply the disinfectant, whether by spray, wipe, or immersion, can influence how well it works. Keeping these points in mind helps us maximize the disinfectant's effectiveness and ensure a safe, clean environment. Let's talk about some of the major limitations of this disinfectant. First, it has no sporicidal activity, which means it cannot eliminate bacillus spores. This is a key point because spores are often resistant and can be a real challenge in sterilization processes. Another limitation is the evaporation issue. The disinfectant tends to evaporate quickly, which reduces the contact time necessary for effective disinfection. If it evaporates too fast, it might not have enough time to do its job properly. We also need to consider the interference caused by organic loads, like blood or dirt. Organic material can reduce the effectiveness of the disinfectant, making it less reliable in real-world situations where organic matter is present. It's important to remember that this is not a sterilizing agent, it's only a disinfectant. That means it can kill many microbes, but it doesn't eradicate all forms of life, especially spores. So, while it's useful, it shouldn't be relied upon for sterilization purposes. Understanding these limitations helps us use this disinfectant appropriately and highlights when we might need to consider other options for more critical sterilization needs. Let's talk about the particle generation risk associated with aerosol or spray IPA. One of the critical limitations here is that IPA can actually generate airborne particles itself. This means that when we use it, we might be unintentionally adding particles to the environment, which can interfere with our particle monitoring efforts. This is particularly important because if the aerosol creates extra particles, it can lead to false readings, giving us a falsely high particle count. Essentially, we might think there's more contamination than there actually is, or worse, it could mask real contamination risks that we need to identify and address. This is a significant concern because it can put us at risk of noncompliance with Annex 1, which sets the standards for good manufacturing practices in sterile environments. So, understanding and managing this risk is crucial for maintaining compliance and ensuring the integrity of our contamination control processes. Let's talk about risk mitigation from a regulatory perspective. One effective strategy is to replace aerosols with spray and wipe methods. This not only reduces the risk of inhalation or exposure, but also provides more control during application. Speaking of control, implementing controlled application methods is crucial, ensuring disinfectants are used properly to maximize efficacy and safety. Another important point is disinfectant rotation. Using different agents, such as hydrogen peroxide or peracetic acid, helps prevent the development of resistant strains and maintains the effectiveness of our disinfecting protocols over time. It's a proactive step to keep our processes robust. Monitoring is equally vital. We need to keep a close eye on residues left behind and track environmental monitoring trends. This helps us identify any issues early and verify that our cleaning procedures are working as intended. Finally, validation plays a key role. We must validate hold times and stability to ensure disinfectants remain effective throughout their intended use. This comprehensive approach, covering use, implementation, monitoring, and validation, supports both compliance and safety, aligning with our overall goal of maintaining a secure and effective environment. Let's take a closer look at the comparison between IPA and sporicidal agents. First, it's important to understand that IPA, or isopropyl alcohol, is a widely used disinfectant known for its quick action against many microbes. However, when it comes to spores, which are particularly resistant forms of microorganisms, IPA isn't sufficient. It doesn't reliably kill spores, which can be a concern in certain settings. On the other hand, sporicidal agents are specifically formulated to target and eliminate spores effectively. These agents usually have a longer contact time and more potent chemical properties to ensure spores are destroyed. So the key takeaway here is that while IPA is great for general disinfection, for environments where spores might be present, like healthcare settings, you need to rely on sporicidal agents. This distinction is crucial in maintaining a high standard of infection control and ensuring safety. Connecting this to our overall theme, Choosing the right disinfectant depends on understanding what microorganisms you're targeting, whether it's bacteria, viruses, or spores. So to wrap up, let's talk about 70% IPA. It is an essential disinfectant in aseptic processing, but it's important to remember that it has its limitations. While it plays a crucial role, especially for routine microbial control, it's not enough on its own to fully prevent contamination. Think of it as a key component of a broader disinfection strategy. To truly ensure safety and sterility, 70% IPA must be part of a validated disinfection program combined with a comprehensive contamination control strategy. When used effectively within this framework, it helps us maintain the high standards necessary in aseptic processes. For further support, please feel free to reach out to us. We're here to help with any questions or additional information you might need. Thank you so much for your time and attention today. If you have any concerns or need clarification, don't hesitate to contact us. Once again, thank you for being part of this presentation, and we look forward to staying connected.